Hi, I'm Tadeusz Kobus and I'll talk today about Jiffy, a novel linearizable skip list with batch updates and snapshots. This is joint work with Maciej Kogociński and Paweł Wojciechowski. Everybody who ever did even a little bit of concurrent programming knows that concurrent programming is hard and error-prone. Thus, whenever possible, we should use concurrent data structures because they offer clear semantics, require no additional synchronization, and we can depend on them in terms of correctness. Quite often, the performance of concurrent data structures directly impacts the overall performance of the entire application. Hence, it is important to do research in this area. So what is Jiffy? Jiffy is an ordered index or a map dictionary. It's 100% linearizable and lock-free and has several unique features. Crucially, Jiffy is the first lock-free ordered index that features batch updates, which are multiple put-remove operations on arbitrary keys that are to be executed atomically. Secondly, Jiffy supports snapshots, which are used, for example, by range scans. Jiffy's snapshots resemble to some extent read-only ACID transactions because they allow the programmer to repeatedly access arbitrary keys using lookups or range scans. It is in contrast to some other systems in which a snapshot is created only to facilitate a single range scan. Moreover, creating or refreshing snapshots in Jiffy is very cheap. Finally, Jiffy's internal structure dynamically adapts to changing workloads for optimized performance. It all means that Jiffy is very fast despite rich semantics. Let's now talk about Jiffy's architecture. Jiffy is implemented as a multi-version skip list. All operations on the linked list, as well as operations related to creation of new versions, are based on compare and swap. Data in Jiffy are stored in immutable containers called revisions. Each revision, here depicted as a triangle, corresponds to multiple key value entries in a concrete version. Typically, a revision contains about 50 key value entries. This allows for better cache locality, so also better performance. Moreover, by altering the sizes of revisions, Jiffy is able to adapt to changing workloads. So for instance, smaller revisions are better in update-dominant workloads, whereas larger revisions are optimal for read-dominated workloads. Because Jiffy stores data in revisions, it means that the index must grow and shrink in a different way than in an ordinary skip list. In Jiffy, it happens by splitting or merging the nodes and revisions. Typically, under a single node, which encompasses a range of keys, starting from the key stored in the node and ending with the key stored in the adjacent node, we have regular revisions, here blue triangles, which form a simple linked list ordered from the most recently added revision to the oldest one. However, occasionally we also have special revisions, depicted here green and red, which are created when nodes split or merge. These special revisions join chains of revisions from different nodes. Each revision maintains a version number, which is used to order revisions and facilitate snapshots. In a concurrent environment, the easiest way to generate version numbers is by using an atomic counter. However, this approach does not scale past few concurrent threads because the counter becomes the point of contention. Therefore, in Jiffy, we use a different approach. To generate version numbers in Jiffy, we rely on a cycle-level resolution clock, which, for example, on x86-64 is provided by the timestamp counter register. Reading TSC is very fast because it doesn't involve a system call. In our test, reading TSC takes only about 10 nanoseconds. Now, because Jiffy is implemented in Java, we don't access TSC directly. Instead, we rely on Java's standard system nanotime method, which internally uses TSC on popular JVMs for x86-64. On other platforms, such as Apple Silicon, system nanotime relies on a similar mechanism and is as fast. Crucially, system nanotime is thread safe and is guaranteed to return a monotonically increasing 8-byte integer. By using system-provided timestamps to generate version numbers means that there is no contention on the actual creation of version numbers. The Jiffy's versioning scheme allows revisions created by independent concurrent updates to have the same version number. However, revisions that are linked under the same node are guaranteed to have unique version numbers. As I mentioned earlier, a snapshot is represented also by a version number, so as a timestamp. It means that creation of a snapshot is a very fast operation and takes a constant amount of time. So how do we use version numbers to provide lock-free batch updates? To explain that, let me start by describing a simple update, so a put or remove operation. So to perform a simple update, first we need to traverse the index to find the appropriate node, which means a node whose range encompasses the key we want to update. We traverse the index as in an ordinary skip list. Then, to guarantee lock freedom, we complete all pending updates in this node. Next, we copy the head revision, which is the most recently added one, and apply the update on the revision. recall that each revision stores multiple key value entries. So for instance, we update the value of one of the keys. In the fourth step, we assign a so-called optimistic version number to the revision, and then add the revision to the list using a compare and swap. Once the revision has been added to the list, we replace the optimistic version number with the final one. This also happens through a compare and swap. Finally, we iterate over the revisions in the list and perform garbage collection by getting rid of revisions that are no longer needed. So you can see here that the version number assignment process involves two steps. This is required to facilitate batch updates. The basic logic of performing batch updates in Jiffy is very similar to performing a simple put or remove operation, but obviously sometimes we need to create multiple revisions under different nodes. To guarantee atomicity of a batch update, the version numbers are not stored directly in revisions which are created during this operation. Instead, a version number is stored in and accessed through a batch descriptor, here depicted as a red circle, which is referenced by each revision created by the batch update. The optimistic version number is written to the batch descriptor before the first revision of the batch is added to the index. We replace the optimistic version number with the final one using a compare and swap only after all put and remove operations from the batch are applied to the index. Note that the batch descriptor also stores information about all put and remove operations to be performed with the batch. This allows other threads to complete the batch update and so to guarantee lock freedom. As I already mentioned, this two-step version number assignment process is there solely to facilitate batch updates. We distinguish between optimistic and final version numbers by the sign of the number. When the version number is negative, it means that it is an optimistic version number. Moreover, we enforce the following constraint. The final version number is always greater or equal to the absolute value of the optimistic version number. It means that whenever we encounter a revision with a negative version number, we know that there is a pending update operation that we might have to complete to guarantee lock freedom. Some operations, such as a simple get, can safely skip revisions from uncompleted updates and just return the value from the first encountered revision with a positive version number. Since a snapshot corresponds to a certain version number, reads on the snapshots can skip revisions whose absolute value of the version numbers are too high. So here you can see how many compare and swap operations are needed to perform put and remove operations, as well as batch updates consisting of n operations. A simple put operation requires two compare and swap operations, one to add a revision to the list under some node, and then one to replace the optimistic version number with the final one. We have to perform similar operations when we want to remove a key that is present in the index. When the key is not present in the index, no changes to the index are necessary. For a batch update, the number of compare and swap operations that we need to perform naturally depends on the number of revisions created. Minimally, a batch update will create a single revision and requires two compare and swap operations, similarly to a simple put operation. In the worst case, when each key from the batch is managed by a different node, we need to create n revisions, and so in total we have to perform n+1 compare and swap operations. Each node split or merge requires two additional compare and swap operations, as I will now show. Let's start with a node split. For now, assume that there is no pending update. All we want to do is to split node K into two nodes, each managing half of the original range of key K. Note that under both nodes K and R, we already have some revisions, as it's always the case. We start with the node split operation by creating two split revisions, left and right, as depicted here with green triangles. Each revision has half of the entries of the sole revision originally linked to the node K. Let's say that after the split, node K will manage key range from K to O, whereas the new node will manage key range from O to R. Both revisions reference each other and share the same successor. We use compare and swap to add the left split revision to the revision list under node K, as in figure B. In the next step, instead of creating a regular node O, we create a special node depicted with a green circle, which we call a temporary split node. As I will explain in a minute, this is necessary to avoid an ABA problem. Once the temporary split node is created, we can use compare and swap to swing a reference from node K to node R to a temporary split node. Now we can create the regular node O. Note that the right split revision is set as the first revision of its revision list. Finally, we swing the reference between node K and the temporary split node to node O and remove the temporary split node. So far, we had to perform 3 compare and swap operations in step B, D, and F. However, remember that we assumed that there is no pending update, and we said nothing about version numbers. In practice, such a node split is always streamlined with an update. In other words, a node split happens when we realize that performing an update operation on node K, so for example, a put operation on key M, would result in a too large of a revision. Hence, the first compare and swap operation in step B can be counted towards an update. Then we have 2 additional compare and swap operations in steps D and F, and the one that sets the final version number, which also can be counted towards a regular update. Hence, in total, a node split requires 2 additional compare and swap operations. Now, let me briefly get back to the reasons behind having a temporary split node, so this green circle. Without the temporary split node, the ABA problem would be possible when the thread that creates the split revisions, so the green triangles, is preempted before it creates the regular node O. Then a different thread might come and help with completing the operation by creating node O. Later on, when the new node O is merged back to node K before the first thread resumes its operation, node O will be created for the second time incorrectly. With the temporary split node, the ABA problem is still possible, but we can recover from it by checking whether the version number in the split revisions is the final one, and consequently, whether the split operation has been completed. Now let's look at the node merge operation. As before, assume that there is no pending update. All we want to do is to merge node O into node K so that it will manage a key range from K to R. We begin a node merge operation by adding, using a compare swap operation, a special revision to the node that we want to merge. The special revision, here marked with a black triangle, is called a merge terminator. No other revision can precede a merge terminator. In other words, any concurrent thread that encounters a merge terminator knows that there is a node merge operation going on and that it needs to be completed before the thread can carry on with its updates. In the next step, step C, we create a new so-called merge revision, here depicted as a red triangle that encompasses the entries from the revisions at node K and the node O. Note that a merge revision has 2 successors and also references the merge terminator. A merge revision is added to the head of the revision list at node K using a compare and swap operation. Then we can use compare and swap again to swing the reference to node O at node K so that it points to node R. This way we remove node O from the index. Finally, we can garbage collect node O together with the merge terminator. As with a split node, a node merge is also streamlined with an update. It means that we commence a node merge if a potential update at node O, for example, a removal of key P, would result in a new revision whose size is below a certain threshold. These additional compare and swap operations that we need to perform come in step B and D. Let me quickly get back to the merge revision, which, as I said, has 2 successors. When a get operation iterates over the revision in the list at some node and encounters a merge revision, we use the key we are looking for to decide whether to go to the left successor or to the right successor. A range scan proceeds left and right successor, processes left and right successors recursively. Before I go to the next slide, note that a node merge operation prioritizes a node with a lower key because whenever we encounter a merge terminator, we need to complete a node merge before we can carry on with other updates. The same goes for a node split operation. If we encounter, let's say, a temporary split node, we need to complete the node split before we can perform other updates. Such a consistent scheme is crucial to avoid live locks. For the same reasons, batch updates in Jiffy proceed from higher keys to lower keys as shown in the slide. The orange revisions are already added to nodes R and M, but not to the node E. Because a batch update proceeds from higher keys towards lower keys, multiple index traversals might be needed to complete the operation. However, the cost of multiple traversals is negligible compared to the cost of creating and adding revisions to the appropriate nodes. This approach allows us to avoid creation of unnecessary revisions. Let's assume that a batch update proceeds in an opposite order, so from lower keys to higher keys. Then it is possible that a batch update adds a revision to some node I, and then proceeds to node M that directly follows I, as in the slide, and decides to perform a node merge operations on node M. Consequently, an additional revision would have to be created on node I, which is suboptimal. Now let's look at the layout of a single revision. Each revision consists of 3 arrays. The first 2 store the key value entries ordered by keys, so to provide cheap range scans. The additional array, hashes, allows us to speed up key lookups. It contains 2 AND entries that can be used as references to the key array. Let's say that we are looking for the key fog. First, we calculate the hash of the key. Assume that the hash corresponds to entries 6 and 7 in the hashes array. Under those entries, we can find the indices of keys whose hash is equal to the one we've just obtained. If there is no such key, the entry is empty and we can return early. So firstly, we check if fog can be found in keys at 1, and if no, if it can be found in keys at 3. If we are successful, we simply return the value from the values array at the same index. We use binary search as the fallback. As I mentioned earlier, Jiffy dynamically adapts with this structure to changing workloads by altering the sizes of revisions. To this end, we compute the desired sizes of all revisions independently. We do so by estimating the time threads spent performing read and update operations in each revision. We then map the ratio of these values to a key range of 25 to 300 so that the frequent updates correspond to smaller revisions and frequent reads to larger ones. Again, we extensively rely on timestamps that can be obtained very cheaply. Now, why does a fixed range of 25 and 300 works in practice? Firstly, note that we implemented Jiffy as a generic Java data structure, which means that revisions store only references to the actual key value objects. Consequently, the revision size in bytes does not depend on the key value type. Secondly, we observe that creation of a very small revision, so smaller in size than 25 entries, is not much faster due to some constant overhead in Java. On the other hand, increasing the number of entries within a revision past 300 provides diminishing gains on the lookup times and starts to become problematic for updates. So here you can see Jiffy against the state-of-the-art competitors. Note that currently the only other indices that offer batch updates similar to Jiffy are log-based. All systems do support linearizable range scans, but not generic snapshots. The only exception here is Java CSLM, so the ubiquitous concurrent skip list map from the standard Java library, which we use as a baseline. The indices marked in blue are part of our experimental evaluation. Our performance evaluation is focused on ascertaining the scalability of Jiffy and its competitors on the varied workloads. Crucially, we test simple put and remove operations, as well as 4 types of batch updates that differ in size and characteristics. It means that batches include either 10 or 100 updates, and the updates correspond to a random set of keys or a range of subsequent keys. Note that I will show only some results from our paper. Here you can see the throughput in millions of operations per second of the indices in the function of the number of concurrent threads in 5 scenarios. In the first scenario, all threads perform only simple put and remove operations. Compared to other indices, updates in Jiffy, see the blue line, are more costly because Jiffy requires 2 compare and swap operations per update to facilitate batch updates. However, despite that, it is over 50% faster than Java concurrent skip list map and only slightly slower than the best of the competitors. You can see here that the log-based indices, so the contention-aware trees marked by the pink and gray lines, fail to scale past 64 threads. Now let's see what happens if we start adding lookup operations to the mix. In this second scenario, 75% of threads perform get operations, while the remaining threads perform put and remove operations. Now, Jiffy is almost as fast as the fastest index here, and twice as fast as Java concurrent skip list map. The results in the third scenario showed that the get operations are fastest in Jiffy. In the last 2 scenarios, 25% of threads perform range scans that are either short or long, which means that they iterate over 100 or 10,000 key value entries. Note that in Jiffy, as well as some other systems, a range scan returns entries one by one. This is why we count a range scan over 100 key value entries as 100 operations. Range scans are extremely fast in Jiffy. In such a mixed scenario, Jiffy tops all other indices despite offering rich semantics. Now let's take a look at the scalability when all put and remove operations are performed within batch updates. Each batch update consists of 100 operations, so batches are large. Naturally, we compare Jiffy only against indices that also support batch updates, so binary search tree-based indices called CAAVL and CASL. Both these indices are log-based, unlike Jiffy. Note that we examine two extremes: batches consisting of completely randomly chosen keys, dotted lines, and batches with sequential keys, dashed lines. The former one typically creates 100 revisions each. The sequential batch updates result in a couple of new revisions and so can be performed much more efficiently. In all cases, Jiffy manages to outperform its competitors. The advantages of the log-free nature of Jiffy is especially visible in the first scenario with batch updates that modify randomly chosen keys. Here, Jiffy's performance is up to 7.5 times the performance of competition, which cannot scale due to contention on logs. Jiffy's source code is very complex because of its features and its log-free nature. To aid the development of Jiffy, we created a test harness for concurrent data structures, which greatly helped us to detect and remove some extremely subtle bugs from our implementation. During a test, threads collect traces of performed operations and periodically record timestamps. After the test, we use the collected data to construct a large graph in which nodes are the operations and timestamps, and edges are the dependencies between various operations. So for instance, we consider write-write and write-read dependencies, program and timestamp orders, and some constraints related to batch updates and snapshots. We iteratively refine the graph to make it as dense as possible by deriving new edges. And finally, we check if the graph is acyclic. If the graph contains a cycle, then the implementation certainly is not linearizable. We include this test harness alongside Jiffy source code, and we encourage you to check it out. Thank you.